So to solve this least squares type situation where we have an inconsistent system, we had these two steps. First, we were going to find the vector in the image of A that's as close as possible to B, and we've taken care of that. Right now we know that the vector we're looking for is the orthogonal projection onto the image of A of B. So next we need to find some nice way of solving this this equation, ax equals y. And the thing is, actually computing this projection is a bit annoying, right? It would take a lot of work. How we came up with this projection was we found some nice orthonormal basis for Rn, and then we did some big computation. But finding orthonormal bases is kind of annoying. You have to take a regular basis and then do the Gram-Schmidt process, I guess. That's a ton of work. So we'd like to be able to solve this equation without having to actually come up with, without explicitly calculating the vector y, right? Actually finding the vector y is a bit of a pain. So here's what we'll do. So this is what we want to do, right? We want to find x so that ax equals y. We know for sure that this will be consistent because we know that y is in the image of the matrix A. But finding a solution is the same as finding an x so that ax minus b is orthogonal to the image of A. So remember the setup here. Here's the image of A. We have this vector b that is not in the image. Okay, we have this orthogonal projection y, and over in our domain space we have a vector x that the matrix A sends to y, right? So if we can find a vector x so that so that ax minus b is orthogonal to the image of A, well, if we have some vector here ax, right? For most vectors ax minus b is this vector. For most vectors ax, this dotted vector isn't going to be perpendicular to the image. The only vector for which ax minus b is perpendicular to the image of A is if ax happens to be y. So what we really want, right, we could solve this equation, but we'd have to know y ahead of time. But we can get away with not finding y if we instead figure out x so that ax minus b is orthogonal to the image of A. Let me remind you at this point that the image of A is the same thing as the column space of A. Okay, so we want ax minus b to be orthogonal, that is perpendicular to the column space of A. But another way to say this is that we want ax minus b to be perpendicular to every column of A. Right? The column space of A is the span of the columns, so the columns are a spanning set for A. Well, if we can arrange for ax minus b to be perpendicular to every column, then it's definitely perpendicular to the entire column space, the span of the columns. Okay, well, how can we detect if ax minus b is perpendicular to a column? So, how do you detect if things are perpendicular? Well, you check that the dot product is zero. So we want ai dotted with ax minus b. We want this to be 0 for every I. And I guess, sorry, I need a transpose here, right? Because we usually write A as, right, its columns. So its columns are A1 through N, I guess. So, no, I don't want to transpose. Right. So we want each of these columns to be perpendicular to ax minus b, right, which remember is this guy over here. Okay, but the dot product is, right, a nice way to write the dot product is to take the transpose of the vector on the left. So to get this dot product equal to 0, instead we can write a sub I transpose times ax minus b equals 0 for every I. But we can, so this is n different equations that we all need to make equal to 0, but we can actually put these all together, right? This matrix at the left-hand end of this matrix product is a row vector. So when you have I different equations all with a row vector here, you can stack up all of these equations into a single equation, but all of these rows, all of these individual rows become the rows of a matrix. So we get A1 transpose down to AN transpose, like this. And so we want this to be equal to 0. Now this 0 isn't a scalar 0 anymore. Now it's a vector 0. Okay, so we've encapsulated all these n different equations in a single matrix equation. But look at this matrix equation. This matrix right here, that's just A transpose. So we want A transpose times AX minus B to be equal to 0, right? So we need to solve this equation. Solve for x. But now that we have it written as a single matrix equation, we can do matrix algebra to make this easier to solve. In particular, we can distribute the A, or the A transpose. So we get A transpose A times x minus A transpose B equals 0. And then move the A transpose B to the other side. So A transpose A x equals A transpose B. And we need to solve this for x. Now, it might seem that we haven't made any progress, because remember, at the very beginning, what we were trying to solve was the equation ax equals b. And the whole problem was that this equation might be inconsistent. So it seems like, well, we've just replaced one equation with another equation. But the key thing here is that this new equation is guaranteed to be consistent. There will always be a solution. Why is that the case? Well, remember, solving this equation is the same thing as solving this equation. It's just that we don't have to explicitly find out what y is, right? That's why this shortcut is so great. We don't have to explicitly calculate the vector y. But solving this new equation is the same thing as solving ax equals y, and we know that ax equals y is consistent because y is in the image of b, is in the image of a, so there has to be a solution. So since ax equals y is consistent, this new equation is also guaranteed to be consistent. And the nice thing about this new equation is if you already know a and b, this equation is very easy to write down and it's very easy to solve, right? All you have to do is figure out what this new equation is by calculating some matrix products, and then you're solving a regular old system. This new equation is called the normal equation associated to the original equation ax equals b. So the short version of all of this is to find your least squared solution, solve the normal equation.